So this is video number 2 in a series of 5 videos about graph traversal for A-level. If you haven't watched the first one, watch the first one first because it will give you the introduction for what you need. So in this video, we're going to have a look at the breadth first search. And just a quick reminder with breadth first search, you start at your start node and you spread out almost like a virus. So you've got all the nodes that are 1 step away, all the nodes that are 2 steps away, all the nodes that are 3 steps away, and so on. And what we do, the actual technique we use here, is we put these nodes in a queue. So we start with 11, that's our starting point, and then we'll deal with 11, we'll kind of interrogate 11, and we'll look at all the adjacent nodes, we've got 12. And then once we've got 12, we'll look at all the adjacent nodes to 12, and we've got 1, 14, and 13. Then we'll look at everything adjacent to 1, which is 0 and 2, that's these two. Then we'll look at everything adjacent to 14, the next one in the queue. And we've got 15, and we've got 19. Look at everything adjacent to 13, and we've got 20 and 10. Then we'll go, the next thing in the queue is 0, so look at everything adjacent to that. These will be fourth, right the first time. These will be 4 steps away, so 3 and 4. So check that one out, we've got 3 and 4. Next one is 2, which is up here. What's adjacent to 2? 16 is new, so we'll add that one in. What's adjacent to 15 next, which is just 18. And hopefully by now you get the idea. We're ticking these off one at a time in the order that we found them and looking at the adjacent nodes. To do that, we definitely want to use a queue data structure. So that's what we're going to do. So here is a graph. Again, we're going to ignore the weights, and I'm going to start by writing an adjacency list. An adjacency list is just a list of which nodes are adjacent. That's going to be really helpful. So adjacent to 1, we've got 2 and 3 and 6. Adjacent to 2, we've got 1 and 3 and 4. Adjacent to 3, we've got 1, 2, 4 and 6. Adjacent to 4, we've got 2, 3 and 5. And adjacent to 5, we've got 4 and 6. And adjacent to 6, we've got 1, 3, 5. Now this exercise has 2 purposes. The first one is to help us with the algorithm that we're going to see in a second. The second purpose is this is a way to store a graph on a computer. You can either store it using an adjacency list or an adjacency matrix. I'm not really going to cover that in this video. That's another topic for another day. If you want a bit more on that, Isaac Computer Science, there's some really good resources. But the way you represent a graph on a computer, we don't represent it as the drawing. We represent it as an adjacency list or an adjacency matrix. So 2 reasons to do that. So now we've got that, here is some code which is from an AQA exam. So this is not code that I've written, this is actually something you would see in a real exam situation, and the blank trace table that we're going to fill in. And at first glance it looks pretty scary and pretty huge, but don't worry, we're going to go through it one step at a time, and we're going to see how we get on. Now the first thing to say is whenever I'm teaching my students, I always say never ever use single character variable names. Your identifiers need to be self-documenting. Okay, so the subroutine, the procedure shortest path, I immediately know what that does. It helps me find the shortest path. The procedure put vertex into queue, I know what that does. It's going to put this vertex S into the queue. Fine. But variable names, found, I know what the variable name found means and what it's for. It's telling me whether I've found the target or not. But S and T are awful. V and U aren't great. So why is the exam board demonstrating such bad practice? The main reason they're doing it is because if you wrote all the variable names using meaningful identifiers, it wouldn't fit on the page. And when you tried to print it, you'd have to print it in font size 6. And it's just not very practical for an exam situation. When you're doing your coursework, your NEA, when you're programming in the real world, that's not an exam situation. It's not one of these fake made up experiences that we have. So use meaningful variable names. That said, if you're in an exam or when you're in an exam and you see a piece of code like this try and work out what these letters might stand for, because that might give you some clues as to how things are working. So if I tell you that S is the starting point and T is the target, it's going to be a bit more meaningful. And what we're going to do is we're going to try and get from node 1, so starting point, to node 5 is our target. Now feel free to try it with different starting points and targets and see how it works, but that's what I'm going to do. So if we follow this algorithm, we pass in S and T, 1 and 5, done. And one thing that's not in this code, but would be in an exam question, is that all the discovereds are set to false, and all the parents are set to blank. So we'll just get those ticked off first. So let's go through this algorithm. First, put vertex into QS. So take the value of S is 1, and put the 1 into the queue. 1 can go at the front of the queue because the queue is empty, so we'll put it in front. Then we set discovered S is true. Remember, S is 1. So discovered square bracket 1, discovered 1 is set to true because node 1, our starting point, we have definitely discovered node 1. That's the only node we've discovered so far. And then set found to false because we haven't yet found our target. So we've done those 3 lines of code. Now, if you've done lots of trace tables before, this will be perhaps an unnecessary repetition. If you haven't done lots of trace tables before, or if you're not super confident, it's quite useful to be able to tick off the lines as you've done them. But once we get into this loop here, it's not going to be possible because we'll end up with lots and lots and lots of times around this loop. So what I always recommend is if you're left-handed, put your left finger to the line of code you're working on right now and write on the trace table with your right hand. If you're left-handed, then point to the code with your right hand and write with your left hand. Use your finger to point to where you're up to, and that sounds really condescending, but honestly, it really, really helps. And also, 2 really important rules with trace tables are that you can never go left and you can never go up. Okay, so I've gone and put my 1 and 5 in here, all my falses, and then when I put something in the queue, I haven't gone left. Can't go left, you've got to wrap around to the next line, put it there, never go up. When I fill in this found is false, don't go up to the previous line, just keep going round as though it was a typewriter. You might need to Google what a typewriter is, but as if it was a typewriter, you just keep going, and if you need to change something, go down to the next line and wrap around to the left-hand side again and keep going. But never go left on that line and never go up to a previous line. Those are the 2 golden rules. Trace tables, along with the 3rd golden rule of use your finger to point to the line of code that you're looking at. I can't do that easily on this video, but trust me, I'm pointing with my finger. So we've done these first 3 lines, we're up to this while loop here. While queue not empty, and the queue is not empty, and found is false, then go into the loop and get started. So we'll do that. So next we've got get vertex from queue. So we're going to get the thing from the front of the queue. That's the 1. So the queue is now empty. We're going to take that 1 and store it in V. And V, it's not very meaningful, the letter V really, but V is the node that we are interrogating. So we're going to start by questioning this node and looking at all the adjacent nodes, because we said here, we start at a particular node, and then we look at all the adjacent nodes. Then we look at each node we've got, and we look at all the adjacent nodes. Okay, so we're interrogating this node, and we're looking over here, down here, and potentially down here, but we've actually already seen it. But we'll get to that in a minute. But that's what we're doing. Okay, really important we remember that. So we've got the vertex from the queue. For now, this line of code here, not terribly straightforward. For each vertex U adjacent to V. So let's break that down. We've got a for loop, so we're going to repeat a fixed number of times. We're going to talk about a vertex called U, and that vertex U is adjacent to V. So this is where this adjacency list up here comes in. And what we want is we want all of the nodes adjacent to V. V is 1, so we want these nodes here, 2, 3, 6. So we're going to go around this for loop 3 times. using 2, 3, 6 from this adjacency list. Right, so start with 2. So we're going to set U to be 2. So put that in there. There we go. And I'm going to cross that off while I remember so I don't come back and do it again. It says if discovered U, so if discovered 2, remember U is 2. So if discovered 2 is false, and it is, and found is false, and it is, then put vertex into queue U. Put U, which is 2, into the queue. Queue is empty, so it's going to go at the front of the queue. So that's that done. Discovered U is true, so discovered 2, set that to true. There we go. Parent of U is V, so put the value of V, is 1, into parent U. U is 2, so parent 2. Parent 2 is 1. And again, never go left, never go up, so we're going to fill it in that row. What's parent doing? Parent is telling us how did we get to this node? Where did we come from to get here? If U equals T, well, U is 2 and T is 5. U is not the target. We haven't found the target yet, so skip the if statement. That's the end of that if statement, end of that for loop. So we go back round to the start of the for loop, and we get the next vertex U. So basically we've gone, oh, we've found node 2. So now we do the same thing. Get the next value of U, is 3. So we're essentially going to do this and look at 3. So I'll set U to 3, and never go left, so I'll put it there. And if discovered U is false, if discovered 3 is false, and it is, and found is false, and it is, then put vertex into queue U. Put the 3 into the queue. So 2 is already in the queue. We'll put the 3 in the queue behind it. It's that one done. Discovered U is true, so discovered 3, we'll set that to true. Parent of U is V. Parent of 3 is 1. Parent of 3 is 1. There we go. If U is the target, U is not the target, so skip that. And if end for, background again, get the next value of U. Got to be adjacent to V, so it's going to be 6. So U is now going to be 6. Again, can't go left. Going to go on to the next line. If discovered U is false, discovered U is false. If found is false, found is false. Then put vertex into queue U. U is 6, so put 6 into the queue at the back, so 2, 3, 6. Discovered U is now true, so discovered 6 is true. Parent of U is V, parent of 6 is 1, so parent of 6 is 1. If U is the target, it's not, so end if, end for. We've now gone around all of the vertices that are adjacent to V, so we're at the end of the while loop. So go back around the while loop and see if we go again. So while the queue is not empty, the queue is definitely not empty. It's got 3 numbers in it. And found is false, found is still false. Go again. So get vertex from queue, get and store it in V. So we'll take the 2 out of here. So we've got 3 and 6 left. And put that 2 straight into V, which is over there. That's that one done. So what we're doing, we've gone from 1 and looked at 2, 3, 6. Those are our U's. We've now finished with 1. So we'll take the first one we found, which is 2. And this time, that's our V. We're going to interrogate from there, see where we end up. So we have finished interrogating node 1. We're now going to start interrogating node 2. So we go through the algorithm again. We've got the vertex from the queue. Each vertex U adjacent to V. So what's adjacent to 2? It is 1, 3, and 4. So first of all, set U to 1. And then we've got if discovered U is false. Well, actually, discovered U is not false. We've already found 1, so we don't need to go back again. So that's fine. Skip the if statement. Save us a bit of time. Go back around, get the next one. The next one is going to be 3. So we'll put that in. And if discovered U is false, well, again, discovered 3 is not false. We've already found 3. We don't need to go there again. So we can skip that. Go back around the for loop again, get the next value of U, which is 4. So basically, we're doing this. If discovered U is false, and it is, And if found is false, and it is, then put vertex into Q. So put 4 into the Q. The Q was 3 and 6. The Q is now 3 and 6 and 4 at the back. Set discovered U to true, so we've discovered node 4. There it is. The parent of U is V, so we can put the parent of 4 is 2 this time, because that's how we got to node 4. We came from node 2. And if U is the target, well, 4 is not the target, so skip that. And then we've now finished already going around all of the for loop. So back around the while loop again, get the next thing out of the queue, basically. So we're finished with 2. So we're now going to get the next thing that we found. So Q is not empty, found is false. So get vertex from Q. It's going to be the 3 and put it in V. So this time we're going to interrogate node 3. What's adjacent to node 3? It's 1, 2, 4, and 6. So we'll start by setting U to 1. And as a human being, what you want to do now is fly through this really quickly, going, I know exactly what the outcome is going to be. However, the way to get these right is to be really slow, really steady, and really pedantic, which is exactly what the computer will do. The computer will not go, 1, I know I've seen that one before, and 2, I know I've seen that one before. It will go through the steps, it will ask questions. So we're going to do the same, even though it seems really tedious and boring, because we're more likely to get the answer right. So if discovered U is false, and discovered 1 is not false, so we skip it, go around, get the next one, which is 2. And the question is, if discovered U is false, discovered U is not false. So again, we'll skip it, go around the for loop, and get number 4. If discovered U is false, discovered 4 is not false. So we'll skip that one as well, and then get 6. And if discovered U is false, discovered 6 is false. So it's not false, it is true, I should say. So skip that one again. And we're looking around from node 3, interrogating node 3. There are no nodes that we haven't seen before. Now, again, as humans, you might have predicted that already. You might have looked at it and thought, well, that's obvious. And you're not wrong, but a computer can't see the blindingly obvious. It's got to follow the algorithm. It can't use intuition, can't use inspection. It's got to follow the steps. That's what we're going to do. Because what you might be thinking is, so far we've looked at node 1, we've looked at node 2, we've looked at node 3, bet we're going to look at node 4 next, but you're wrong. And the reason you're wrong is we'll go around the while loop again, and while Q is not empty, and found is false, then we get the next vertex from Q, which is 6, because 6 is at the front of the queue. So we can't go left or up, so we'll take 6 out, we've just got 4 left, put the 6 in V, and actually, because we found 6 before we found 4, we're going to interrogate 6 before we interrogate 4. So what do we do? For each vertex U adjacent to V, what's adjacent to 6? 1, 3, and 5. So we'll start with 1, set U to 1. If discovered U is false, discovered 1 is not false. So skip that. Then we get 3. If discovered U is false, discovered U is not false. So go around again, get the next one, which is 5. And if discovered U is false, discovered U is false, and found is false. So we are going to do the if statement this time. So we're going to put the 5 into the queue. So the queue is now 4, 5. We're going to say discovered U is true. So discovered 5 is true. Parent of 5 is 6. Parent of U is V. Parent of U, 5, is 6. So parent of U is V. And then if U is T, and this time U is the target, so we set found equals true. Again, can't go left. Wrap onto the next line, found is true. And that's the end of that, That's the last thing that's adjacent to 6. If it wasn't, we would keep going. We can't just assume it's finished. Then we go back around to here, check the while loop again. While the queue is not empty, and found is false. Well, found is not false, so we don't do that anymore. We skip that. We go straight to the end of the end while. We're then at the end of the procedure, and then we can stop. So there is your finished trace table with all of your details on. And the way this will be marked, it varies year on year, mark scheme by mark scheme. But typically, you would look at this column and check that the student, sorry, has a queue incorrectly. You would check the discovereds. What you might do is you might kind of check this section first and check that works. And it depends on the mark scheme exactly. But you're looking for things like, is the U column right all the way down? And you would have that printed in the mark scheme. So that's what we're looking for, and that's how to do it. And what we've done is we've started at 1 and looked what's adjacent to 3, 6. That's kind of here. You can see we've populated that queue. We've then gone to 2, taken the 2 out. What's adjacent to 2? Well, we can add the 4 in. Once we've done 2, we'll look at 3. So take the 3 out. That's down here. There's nothing really new, so that's not very helpful. Take the 6 out. Interrogate from the 6. What can we see from 6? Well, we can now find a route to 5. And then because of that, we've found our way out. And we've found, to get to 5, we came from 6. To get to 6, we came from 1. So the shortest way to get to 5 is to hop to 6, hop to 5. And it is 2 steps to find our way out. Okay, and that is how to do one of these trace tables. It's quite long-winded. This video is already pretty long. And it seems like you could probably do it a bit quicker, and you definitely can. I've deliberately talked through it relatively slowly. Too quick, go through it again, and just keep pausing till it makes sense. There are a couple of examples. So here's an example. And what you could do is you could pause the video, take a screenshot, and print it out and have a go. And once you've had a go at that one, here is another one. And again, you could pause the video, take a screenshot, have a go. And I haven't got the answers on here. If I get round to it, I'll put them in the YouTube description-y stuff. But I'm not promising to get around to that super quickly. But you'll kind of get a feeling for whether you're doing it right or whether you're getting stuck. Maybe get 2 or 3 of you to have a go independently, compare your answers, see if you can see if they start to diverge, where are they diverging and who's gone wrong. One thing to say very quickly with these is I have labelled the graphs A to E rather than 1 to 5. It's not ideal, I know, but if you just translate A to E to 1 to 5 in your head, you'll be able to still follow the same algorithm. Give that a go. And then for the next video, I'll do exactly the same for depth first search. And the very last thing to say is if you're finding this super confusing and tough, when I do this with students, they usually find when we do depth first search, next they find it a little bit easier because they've done this. And so maybe if you're super struggling, have a go anyway, then go do depth first search, and then maybe come back to this, see if it's suddenly got any easier. But best of luck.